The forecast window closes 12 minutes early. The detection remains active anyway. An orbital simulation rotates slowly across the display, while prediction markers slide past positions where no transmission should exist yet. One analyst clears the corrupted sequence and starts recalculating the arrival model. The next signal appears before the software finishes rebuilding it. Sedna moves slowly enough that meaningful timing drift should take centuries to emerge. The prediction windows are not supposed to change inside a single observation cycle. This one keeps breaking. The software rejects the new transmission for 4 seconds, then quietly accepts it. The replay stops 3 seconds before the signal should end. A technician drags the timeline backward and runs it again. Same pulse spacing, same silence between bursts. Sedna is already beyond most meaningful solar control, drifting through a region where sunlight barely reaches at all. Yet the waveform on the monitor behaves like it never left. The timestamps change. The pattern does not. Older telescope recordings from the early 2000s sit beside captures taken years later. Sedna drifts slowly against frozen background stars, almost disappearing into orbital darkness. But the pulse spacing barely changes. No visible degradation. The pattern stays intact longer than it should. Nothing that looks like ordinary interference slowly breaking apart across distance. The playback pauses again. Nobody says the word signal yet. One recording overlays another. The peaks align too closely. A few frames drift apart near the end, then pull back into synchronization just before the transmission cuts to silence. Sedna can travel more than 11 billion kilometers from the sun. Past a certain distance, sunlight weakens into almost nothing. Light arrives hours later than it does near Earth. By the time a signal arrives, Sedna is already somewhere else. But the timing keeps returning as if distance never entered the equation. NASA has tracked Sedna since 2003. Every year, it moves farther from the sun. The waveform still loops almost perfectly. The forecast window closes 12 minutes early. The detection stays active anyway. A pale orbital simulation rotates slowly across the monitor, tracing Sedna's path far beyond the Kuiper belt, while thin timing markers slide past expected alignment positions. One analyst zooms into the prediction grid, checks the incoming timestamps again, then removes an entire section of corrupted data from the sequence. The next signal arrives before the software finishes recalculating. Sedna moves slowly enough that most orbital models barely change within a human lifetime. Caltech models have tracked its orbit for years because timing drift at this scale should take centuries to become visible. The prediction windows are not supposed to move at all. This one keeps breaking. A new detection appears under a different orbital angle, while the previous forecast is still labeled impossible. The orbital simulation keeps rotating behind the incoming detections. Thin white lines pass across the orbital path where the signal should not exist yet. Nobody stops the incoming feed. Nothing else in the system starts failing. The clocks remain synchronized. Telescope positioning stays accurate. Distance calculations continue updating normally. Only the arrival times keep slipping outside the expected windows by amounts that should take decades to appear. Another early transmission appears. The software rejects it for nearly 4 seconds before quietly accepting the transmission anyway. The grass stopped drifting. For the first time, the spacing settles into a clean, predictable rhythm while reflected radiation models unfold slowly across the display. Thin arcs of delayed sunlight move outward from the sun, strike Sedna's icy surface, then continue back toward Earth through deep space. The reconstructed timing suddenly looks reasonable. Sedna moves near the limit of useful real-time observation. Sunlight can take more than 10 hours just to reach the object one way. By the time reflected radiation returns through deep space, the original event may already be over. Inside the clean datasets, the intervals begin matching delayed reflection patterns almost perfectly. Signal graphs smooth out. Missing archive segments begin appearing again inside the rebuilt sequence. No one in the room reacts much. The reconstruction continues running anyway. NASA filtering procedures for distant signals already remove corrupted intervals automatically, especially when detections overlap with weak background interference. On screen, the repaired model keeps matching the incoming sequence almost perfectly. A technician leans forward and removes several timestamps from the lower corner of the display. The animation continues uninterrupted. For a few seconds, the system behaves normally again. Sedna drifts through darkness. Reflected radiation returns in delayed intervals. The spacing remains stable enough to predict again. Then the deleted timestamps briefly return inside the raw archive feed. The model still works! Those intervals just are not supposed to exist there. The mismatch remains after the archive correction. Nobody speaks while the older Deep Space Network logs scroll upward beside the cleaned release files. Detection times, relay confirmations, observatory routing records. Thin gray timestamps drift slowly apart across the screen, like two different timelines are being compared. Sedna is far enough away for observation delay to distort sequence itself. One pulse sequence appears in the raw observatory logs before the solar event later used to explain it. The reflected radiation model still sits open nearby, but the ordering no longer matches. Analysts stop scrolling and move backward through the archive again. The earlier timestamp stays there. Radio transmissions from Sedna can take more than 10 hours to reach Earth, depending on orbital position. At that distance, observation arrives long after the event itself. But this sequence does not arrive late. It arrives early. The release dates and original detections continue separating as more records load into the archive. One observer checks the synchronization source against archive timing references, while another compares relay confirmations from different stations. The verification holds. No corrupted clock, no transmission overlap, no duplicated entry. The pulse pattern predates the event that supposedly created it. The comparison remains frozen on screen for several seconds after that. Cause and observation have changed places. The observatory is empty by the time the final transmission arrives. Humans may still be observing a version of Sedna that no longer exists. Outside the windows, the desert remains completely black, except for a few distant facility lights. Inside, the recording systems continue running unattended, while archived deep space observations cycle silently across different monitors. Telescope images update slowly, while new signal confirmations continue appearing. Tiny timestamps drift farther apart as the data continues traveling inward from the edge of the solar system. Eventually, almost nothing visible remains except delayed evidence. Deep space communication already assumes that distance breaks immediacy. Signals weaken long before they arrive. Entire conditions may end before Earth even receives confirmation they existed. Sedna remains visible only through light and radio evidence that left it long ago. The pulse spacing returns one more time. No observer reacts to it now. The room stays empty while the system continues recording automatically. A thin waveform moves across the screen, pauses briefly, then repeats again over low background static. Billions of kilometers away, the original condition may already be gone. The delay never closes. The observation never becomes current. Every distant object humans study is already part of the past by the time it is seen. The transmission ended long before anyone understood what they were seeing.